course, and we have the session 1. Our topic for today is about pre-earthquake processes and its impact on environments. And we have Prof. Katsumi Hattori from Chiba University, Japan, to deliver her course materials for today. So the moderator for today is Pak Wahyudi Parnadi. So we are welcome Pak Wahyudi Parnadi and Prof. Katsumi Hattori.
Okay, thank you. Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. Our speaker today is Professor Katsumi Hattori. He is now Director of Center for Environmental Remote Sensing at Chiba University, Japan. So he has graduated from Department of Sciences, Graduate School of Science, and received or obtained a Doctor of Engineering. And now he is a full professor at Chiba University. He has more than 189 publications on ResearchGate and over 2,947 citations. So this is too much for us. Yeah, he is geophysics, so he has a background and expertise in geophysics, seismics, exploration geophysics, applied geophysics, earthquake, earth sciences, tectonic, and invasion. And about his latest projects, pre-earthquake processes, a multidisciplinary approach to earthquake prediction studies, multi-instruments based on observations and validation of the physical model of the lithosphere, atmosphere, ionosphere, magnetosphere coupling, and an interdisciplinary approach for earthquake modeling and forecasting. And last but not least, Professor Hattori and friends has produced or issued a book about earthquake, about pre-earthquake processes. I think this is a hot topic, yeah, especially for us who work with earthquake processes, earthquake prediction, etc. So, yeah, before the presentation begins, let me inform how the presentation will be going on. First, Professor Hattori will be invited to present material. After that, there will be question and answers with quick processes questions, and followed by conclusion. And I hope Professor Hattori can give us closing remarks. I think, yeah. Now, allow me to welcome the speaker, Professor Katsumi Hattori, to deliver his presentation. Professor Hattori, the floor is yours.
Okay. Thank you very much, Professor Yudi. I'd like to share my screen. Please permission to share screen. Please give me permission. Okay. So now you can see my screen.
Yes, clearly.
Okay, thank you. Okay. Selamat pagi.
Selamat pagi.
Nama Katsumi Hattori, Chiba University. It's correct? I don't know, but it's okay. The title of my talk today is Pre-earthquake process and its impact on environment. And Professor Yudi introduced me very nicely, and I prepare by myself, but I don't need to tell about it. Okay, anyway, this is my face, and this email here. So if you have any question, you can contact me directly. It's very welcome to this one. Before I start my talk, briefly, I'd like to introduce you our Chiba University. So this is some view of our university. You can, how to say, this URL gives us some more information about it. Anyway, our university located near Narita Airport, which is a gate of the world, Japan. And the philosophy of our Chiba University always aim higher. And feature of Chiba University is we have many faculties, and we have liberal arts and science also. And we have world-class education research environment in the graduate school. Also, we have a very good place to come to Tokyo and Narita International Airport. So you can come to our university after COVID-19 problem solved. We are very welcome to you. We have 4 campuses in here. Our main campus is top one, Nishichiba campuses, which Yudi-san visited our lab. And this is the number of faculty members. We have about 3,000 staff, teachers, and some technical staff. Okay, 3,000. And the number of students is about 15,000, including graduate student and undergraduate student. And we have 9 faculties in undergraduate. So the science, engineering is mainly you'd like to, how to say, you have interest. Also, we have medicine and pharmacy. And the graduate course, science and engineering merged. And one course we have. This is for master course. Doctoral course, the similar structure we have. And we have many sister universities. This is as of 10 years ago. We have more than 300 sister university and sister institutions. ITB is one of them. And also we have a research project. Here, ITB is giving help. So our CERES is a Center for Remote Sensing, has also some project with ITB. And we accept some overseas students, mainly from Asia, from China, Korea. Of course, we have some Indonesian students. And this is our office overseas. One of them, we have Indonesia. It is located at University Indonesia. So if you have interesting, if you'd like to have some information about university, you can visit University of Indonesia and you can get some information from the desk. This is the last view of Chiba. So we have very good 4 seasons. Spring, this is Chiba Castle, and this is Sakura Blossom. In summer, we have fireworks. In autumn, we have the red leaves, and this is a Buddhist temple. So this is a very good season, Japan. So if COVID-19 problem is solved, you can come to Japan to study or sightseeing. We are always welcome you. So this is a brief introduction of our university. So if you are interested, you can come to our university. Okay, now I'd like to start my topic related to the pre-earthquake process and its impact of environments. Outline of today's talk is first, I'd like to give some introduction and I give you some early warning system, earthquake early warning systems, and then short-term earthquake forecast. And I'd like to say something about the creation of next generation of early warning information system for effective earthquake, tsunami, crisis, responsive navigator, including the forecast. So this is a talk what I'd like to say today. So this map indicates the earthquake activity in the world as of 1993, 1 year data is given here. You know, earthquake happen in limited areas, like boundary of the plate. Japan is here, Indonesia is here. Our country overlapped by the epicenter, so we cannot see islands. Anyway, we cannot escape from the earthquake disasters from this figure very clearly. This is the forecast activity around Japan. A color indicates depth. Okay, here is some activities of active area is given here. Anyway, this activity is related to the plate motion, Pacific plate subducting into the Eurasian plate. So our country is many earthquake. And this is a cross-section of the northeast part of Japan. Subducting Pacific plate is given here. So we can see very clearly the boundary due to the epicenters, hypocenters. So if we take the only large earthquakes over 100 years, here we show the activity magnitude greater than 7 and shallow one. Japan island given here, dot indicates their epicenters, hypocenters. You see, near the seashore, we have many large earthquakes, mainly subducting large earthquakes. So this is very similar to the Indonesian situations. Okay, how about Indonesia? What is seismic activity in Indonesia? So this is 10 years data is given here. Dot indicates the earthquake. Okay. You cannot see Indonesian islands because of seismic activities. Red color indicates shallow one, and dark color indicates the deeper one. Clearly, this is Sunda Strait given here, the shallow, deeper northern with northward. And this activity is somehow related to your tectonic setting. If we take magnitude greater than 6 with 100 years, still you can see the active, very active in all over Indonesian regions. The black line indicates your tectonic lines. Okay, you can see this activity is along these tectonic lines. If we take magnitude 7, okay, anyway, you have many large earthquakes along your islands. There is some inactive areas here, but maybe this is the gap. In the future, you will have some large earthquake expected. Okay. And also this is your technique pattern using the GPS motion with your plate. Anyway, yes, in the trench, Australian plate subducting to the Sunda plate. Okay, so this is the main tectonic line. And also the eastern islands, this tectonic line is very complicated, but you have some related of this complexity. Your earthquake pattern is very complex. And also this kind of the subducting large earthquake gives tsunami. This is a simulation of 2004 tsunami by NOAA. You can see this is hypocenter and the tsunami propagate Indian Ocean and to all over the world. And this huge tsunami killed many people. Anyway, this is one of the world disasters in this decade. Okay, this is a photo from Thailand at this tsunami. Okay, anyway, it is very. This shot is by U.S. armies at tsunami attack at village after tsunami attack. Most of the house wiped away. And this is also again tsunami at Thailand. This kind of happened. How about China? China doesn't have any subduction. But this is a deformation, cluster motion by GPS is given here. In China, large deformation is given by these areas. Why? Because Indian continent collapsed with the China mainland, and they create the Himalaya mountains. And this eruption give us some earthquake activities. Okay, here. And this is seismic activities in China. Actually, this area, western part of China and near Beijing, so they have some active regions. And Sichuan earthquake in 2008 with magnitude 8 happened here. Just the boundary between the active area and inactive areas. And more than 10,000 people, 100,000 people killed. Casualty in China by natural hazard is given here. In 20 statistics shows the casualty in earthquake is one of the most severe. Maybe in Indonesia, maybe I think same. And this is the damage of the earthquake in Japan and in China. The earthquake size is mostly same in magnitude 7 in China and Japan. What is difference is the morphology of after the quake. In Japan, the building lay down, but its shape as it is before. But in China, completely collapsed. And deaths in Japan was 28. In China, more than 200,000 people killed. So this is different. This is a simulation by JICA. If M6 earthquake happened in Tehran, in Iranian cities, what happened? This is the original cities. After the quake, the building collapsed completely, and many people killed. They expected. Why this happened? In Iran, the building made up by brick and maybe collapsed completely like this one. In Japan, we have mainly wooden house. Old wooden house was collapsed. This is the Pakistan, very similar to the Iranian case. So this kind of the architecture is very weak for the earthquake. In Japan, Kobe earthquake killed 6,000 people, and most of them are killed in their own house because this happened early morning. And in Japan and in Indonesia, many subduction earthquakes happened. And tsunami is also the danger. This is a tsunami at Tohoku earthquake 2011. Here is the airport. The tsunami is attacking to the Sendai airport. Okay. Anyway, this is a view. And also after the tsunami, we see this boat is on the roof of third floor buildings. You can estimate what is the height of the tsunami in this region. Actually, this building is far from the seashore, about 1 to 2 kilometers apart. So this ship was transferred from the seashore to the inland areas. Anyway, some seismologists in the US told earthquake don't kill people, building and tsunami do. So it's true. So in Japan, in China, quake was shaking itself didn't kill the people. But colossal building or tsunami took away the lives. So it's a problem. So the government or seismic society issued priority is structure issue. Then, not only saving people's life, most problems generated after the quake, such as this one, will be much less if structure damage are less. I think it's true. Maybe everyone agree this idea because structure, architecture is very robust for shaking. It's good, but it is very difficult. All building or all architecture to save for shaking. So it costs very much. Also, it will take many times. So if the short-term earthquake forecast is established, damage to students will be reduced dramatically. So this is also people agree. No one deny. But prediction of earthquake is possible or not? That is the question. Anyway, understand the phenomena and forecast the phenomena is a little bit different. For prediction, to predict further future is rather difficult than close future. For example, so will you have rain in Bandung today? After 5 minutes. Maybe it is very easy. You can see the atmosphere, or you can see sky through the windows. You can identify we'll have rain in soon or not. But will you have rain in Bandung on September 7 today, but 2024, 3 years later? How do you predict? How do you imagine? So maybe if someone use the statistical ways. So you have 100 years, maybe several years report in BMKG. You can check the data, how many days clear, how many days rain, what is percentage. So September 7, 2024, we'll have rain 30%, 50%, something like that. Anyway, long-term forecast, we use the history or experiments, which we call this a statistical method. For short-term forecast, we use precursor signature or okay, anyway, what is it? Okay, the situation now we can understand. So that is important. So this is a difference. For the earthquake, maybe similar, especially for the large earthquake in subducting zone. I mean, the trench, earthquake happen in trench. This is northern part of Japan. This dotted line indicate the trench, Japan trench and the Korea trench given here. This trench, activity of earthquake in this trench divided into some segments. And earthquake happen in segment and segment, by segment and segment. So some earthquake happen, the next earthquake happen, the next earthquake, future earthquake happen in a gap. So this is the gap theory in Japan. In Japan, a Pacific plate is subducting to the Eurasian plate. The speed is 8 centimeters per year. Okay, this kind of tectonic setting. How about Indonesia? So this is the megaquake activities in Indonesia. So 2004, you have Sumatra Andaman earthquake happen. This is a focal region given here. Next year, you have Nias earthquake. And 2007 happened here. So middle of the Sumatra Island, this area. Earthquake happened, but not sufficient energy released. So maybe next large earthquake happen here, or here, or here. So this kind identify the successive earthquake activities. This is a historical experience. And also taking account of the earthquake pattern, we have some probabilic forecasting. This is a kind of the model, RTL model, derived by the Russian scientist. This is a case for the Wenchang earthquake in China. They compute seismic pattern in these areas. Wenchang earthquake happened here. Before Wenchang earthquake, this seismic activity in terms of RTL dramatically reduced, like this way. And Wenchang earthquake happened. So before large earthquake, they have quiescence of the seismic activity like this. For the Sumatra Andaman earthquake, we compute V value. This is also give us the seismic activity in the Sumatra regions. Actually, we compute these areas using the seismicity. Okay. And the result is given here. This is year given here. And Sumatra earthquake, Andaman earthquake happened here. before Andaman earthquake, there is a big drop of this activity. This is also a kind of the quiescence. This quiescence means the stress accumulating in the computed areas. Okay, you can see this kind of the statistical treatment of the seismic earthquake patterns. Okay, I'd like to show briefly what is earthquake. Earthquake is controlled by the tectonic patterns. I mean the plate tectonics. Usually, ocean plate subducting to against to the continent plate. In your case, Australian plate subducting to the Asian plate. And large earthquake happen boundary of these plates. Sumatra earthquake, Nias earthquake is like this type. Also, inland earthquake is controlled by the propagate of this stress to the inland areas. And this, what happened in the plate boundary is given here. This is a schematic view of the plate boundary. This is a subducting plate is given here. This is the plate boundary. And there is asperity. Asperity is hardly contact to the oceanic plate and continental plate. Hardly contacted, okay, locked. And the other place is loosely contacted and easily to move. So usually, before large earthquake, asperity is hardly contacted, but the other plate is moving very fastly. And this part, hardly contacted place, collapsed due to the stress accumulated and large energy released. So this is a subduct large earthquake. And if stress accumulating under the ground, in the ground, there are many gas and fluids. And this fluid or gas usually ionized. Okay, stress change. That the change of the stress, a fluid move one way to another way, or fluid pull up to the air through ground. This kind of fluid motion gives us a direct current or alternative current. Anyway, ionized fluid motion creates the current. This current creates electromagnetic change. If we can detect this kind of the small change adequately on the surface, in the air, space, we can identify, we can observe some change before earthquake. So this is a kind of the pre-earthquake process or precursor. So that is a key point to monitor the pre-earthquake processes. For the large earthquakes, seismologists consider there is a cycle. So this cycle is repeated in 100 years or 200 years in subducting zones. There are 4 phases. One is tectonic loading, due to lateral motion. This is the background time. Okay, the second one is just before earthquake. This is a quasi-static rupture or nucleation. And dynamic process. So this is a earthquake happened. Okay, and this is the aftershock. So number 1, and number 3, number 4, mechanical sensor. I mean a seismic sensor observe their motion clearly. But yellow part, precursor part, or nucleation, seismic sensor doesn't have stable signatures. So this is very important for precursor or pre-earthquake processes. To understand this, we need very, very sensitive sensors or sophisticated networks. The EM sensor, electromagnetic sensor, is suitable to monitor this. Anyway, seismic sensors, after the earthquake happened, so they can see, seismologists can see something to alert. The big quake is coming, not quake, big shaking is coming. So before coming, everyone can escape. Okay, so this idea is early warning systems, namely earthquake early warning systems. This is a schematic view of the early warning systems. In Indonesia, we also try to introduce this system by BMKG. This is the not prediction. After quake happened, quake generate 2 waves. One is P waves, primary wave. The second, the other is S wave, surface wave, okay, secondary wave. There is a difference in speed. P wave is faster. S wave is slower. P wave is small shake. S wave is very big surface motions. They capture P wave arrival using the network of the seismometers. And then they predict the when S wave coming. So there is some difference. Usually P wave is 7 km per second. S wave is 3 km per second. This is a average one. So there are 4 km difference per second. Okay. So anyway, if earthquake happen large in far enough, namely 300, 100 km or so, the time to come the S wave is about few 10 seconds, namely 40 seconds or 30 seconds we have. During in this 30 seconds, what we can do? So we can escape, open the door, something like that. But this R1 system is not perfect because large earthquake in the vicinity of observer is not effective because PS difference, the arrival difference is not so enough in few seconds, something like that. Sometimes before alarm coming, shaking we felt. Japan also. So we need to create the other system to eliminate the to evacuate from the seismic disasters. So this is one of the EM's approach is electromagnetic approach is one of them. Also, tsunami warning system. So you have also important, you also very important for tsunami warning system in Indonesia, Japan also. In Japan, what we doing it here? Using the early warning system, we can estimate the seismic location and magnitude and depth and what type of earthquake happened. And if the epicenter, hypocenter is in seafloor and shallow one, enough magnitude, and what is slip on the seafloor, we can estimate in 1-2 minutes. And we have simulation of the tsunami, many simulation database we have. So we compare the database and epicenter and seismic scale. And then if this earthquake has potential to create the tsunami, they issue alarm. So this is the tsunami warning system in Japan at the moment. And after they issue this alarm, the actual practically tsunami is coming or not, we can check using the tidal gauge data or buoy data. And if the potential tsunami is passing through and come to the seashore, this tsunami alarm is continued. If nothing change observed in these sensors, the warning are canceled. So this is a tsunami warning system in Japan. So maybe in the Indonesia, maybe similar one you created with BMKG. And the current earthquake tsunami information in Japan, not only Japan, but I think that all over the world, the information is only after earthquake happened. Early warning is first, after the quake, P wave, S wave difference, and when the big shake is coming. So this is the first information of the seismicity. A few minutes ago, we can compute the intensity of the earthquake, something like that. And the tsunami warning is given here. Anyway, everything in tsunami earthquake information is after earthquake happened. So without information prior to occurrence. So if we have some adequate information before quake, or we can improve the current system of the early warning, much more better world can be created. My talk is related to this. So this is a concept of the next generation early warning information system for effective earthquake tsunami. Okay, this is the time it's given here. When earthquake happen, this is the occurrence of the earthquake. Okay, maybe some later tsunami is coming. Okay, so we'd like to make sophisticate the earthquake early warning system and tsunami warning system, and also develop the short-term prediction and merged, and we can create next generation earthquake early warning information systems. This is my dream. And once this kind of this navigator is given, so we can negotiate with, we need to negotiate with the client what kind of information we need to extract and what kind of information will be useful for some action to evacuate or protect their important things. So we need to know 1 hour before what kind of information then client can do. 1 day before, 3 days before, 1 week before. This is a normal period. Okay, after the quake and before tsunami coming. So this is in Japanese, so maybe this is much better. Okay, here, the time of earthquake, 1 hour before, 1 day before, 3 days before, 1 week before. Okay, so what kind of information is issued? So what kind of reaction can do? Okay. And tsunami is also. Okay, here is a reaction it's given here. To make this reaction, we need to make the crisis response navigators. Okay, so that is a very important concept. Anyway, important things is extract of timely and accurate earthquake information or data from pre-earthquake signature and earthquake alarm signature and tsunami signatures. So this is very important point of view. What do we need to improve the current earthquake early warning? Current earthquake warning, I told you, this system is not so effective earthquake vicinity of client, observations. Why? Because we use public seismic data. It is not designed for company or client itself. So due to improve this, we need to merge the network system all over Japan and individual sensor systems. And then we can give you some adequate or optimal earthquake early warning to ensure accurate seismic intensity time allowance for stop something. For example, 2 seconds we can give you. That is very important. So we use the public network and also the private network, especially for client. Due to this, we can give you much more better early warning systems. For tsunami, we don't have any information about sea surface change in generation regions. Okay. Before, we have only the information of the seismic source, hypocenters and scale and seismic patterns. This is estimation. And actually, tsunami happen or not, we can see using buoy or tidal gauge. Okay. Important is to understand, to monitor the surface change in seismic regions. Initiation of the monitor using early warning for hypocenter location is very important. But after that, we can use the satellite data using the ionosphere disturbances. So before, after the tsunami, in 7 minutes, the gravity wave propagate to the ionosphere. And the ionosphere part up by the tsunami. And we can monitor, we can detect this motion by satellite, or GNS satellite. And then we can say something can happen here. Combine to the ordinary current system, we can say much more sophisticated data. But the limitation we exist because the gravity wave from the sea surface to ionosphere it takes about 7 minutes. And also in ionosphere, many similar waves we have. To identify this wave is due to tsunami motion. We need about 10 minutes to identify, to discriminate the other possibilities. So it takes about 15 or 20 minutes to identify the system, to identify in system. So this is the limitation, but in principle, it's very important. And if we get this information, we can say much more better tsunami warning. This is the second part. The third part, so this is the last part. So this is a forecast. That's very important. This is brand new. Okay, this is brand new. Anyway, no one or no scientist try this one because seismologist doesn't believe the forecast, but they accepted now precursor signature. Okay, precursor exists, but it is not useful for forecast. This is a altitude of seismologists now. Maybe you agree, but if adequately we use this precursor phenomena, we can forecast the future earthquake in the sense of the probability forecast. So this is a schematic view of the stochastic model, ask a forecast using the stochastic model. So this circle outside indicate the precursor parameters which we would like to see. So one of them is a URF electromagnetic signature, which I told today. And also we have a GPS signature. This is the ionospheric disturbance before the earthquake. If I have a time, I'd like to talk this URF signature and GPS signature, ionospheric signature, because Indonesia has URF sensors, which is operated by BMKG, and also the GPS sensors or ionospheric monitoring by LAPAN or LIPI. You have data, you can apply this idea in Indonesia. Anyway, important thing is we need to make some stochastic model. So this is a very important point. So this is my idea. So we have ETAS models. ETAS model is epidemic type aftershock sequence. This is the best model for predict aftershock. Aftershock means when main shock happened, the aftershock earthquake happened. When main shock happened, this model can forecast aftershock very good. So we use this model using this kind of the precursor signature. We would like to use this model improve to the main shock forecast. So this is our idea. So using for this, we need to the data simulation, the data simulation or machine learning or something like that. This kind of data science will be very important to detect the abnormal signature and also data simulation. So this kind of the how to say this kind of the new science will be very important. And maybe ITB, your team, maybe you are very familiar with this kind of data handling, I think. Okay, this is a view of the seismo-electromagnetic phenomena. This is used for the, in namely, this is a precursor signature, which shows. One of these is a URF EM signature. The other one is ionotropic signature, electron density signatures. I don't say about mechanisms, but we have many hypotheses. If you have questions, I'd like to answer later. And this is a case study for the URF EM anomaly related to the earthquake swarm happened in Japan. Earthquake swarm happened here. Okay, this is the earthquake given here. Swarm activities happen here. Okay, and our station is here, about 60 or 100 kilometers apart from here. And the top panel indicates electric field, middle panel indicates magnetic field. So related to the seismic activity, these two activity enhanced just few months before the earthquake. And also you see there is a seismic peak is given here. And just before this peak, magnetic field, magnetic data gives us some local peak. And this is related to the earthquake we considered. And we have 3 stations in this area and 3 stations here. If we take into account the direction of this kind of signal, the intersection of the signal arrival is here. So maybe this kind of signature came from the epicenter regions. So we conclude. So this is kind of signature highly related to the earthquake. And anyway, this is a case study, and someone said, this is truly related to the earthquake or not. So that is the point. Correlation exactly or not. So that is a very important point. So due to this, we need to very sensitive signal analysis method. Okay, we analyze the data observed here and here and here. Okay, this is our station map as of 2004. But today I'd like to show you this station and this station, this station. Mainly, I'd like talking about Kakioka because this is operated by our JMA rated. So it is open for public. Data are open for public. And the statistical result we can give you. Okay, here, here, here. For magnetic data, ULF2 magnetic signal is composition of several signals. Most intense signal is solar-related actions. Okay. Okay, upper atmosphere signals. That is most important, most intense signal. Second one is cultural noises. The third one, weakest one, is signal from lithosphere. So we need to eliminate intense signals. So this is a typical spectrogram of the observed at the Kakioka stations. Okay. Only nighttime. This is the daily data given here. UT is given here, and this is frequency, and color indicates the activity in dB. So the only this part is quiet, because in Japan, cultural noise is very high. Actually, local time 2:30 and 4 a.m. inactive, because at that time there are many trains, many DC-driven trains are going on. So we use only nighttime data, this period, and 100-second data we use. And this period, we have many outliers due to the solar terrestrial impact. So we compare our station data with Hokkaido data and Kyushu data. This is our target station, Kyushu data, and Hokkaido data. This is signal come from the sun. You see very similar variation you can see. So we can eliminate this signal very easily using the reference stations. Okay, in this case, we use the reference Manbetsu Hokkaido station because the seismically very quiet area here. And this is the case for the earthquake in Boso. M6 earthquake happened here. This is a reference station. This is a target station. You can see before the M6 earthquake, the vertical component activity enhanced. So this is a result here. Okay. And also the near station, we have a slow slip event. At the time, we have very, very unusual structure in even nighttime. This is the normal background case, nothing happened. The reference station and the target station, blue cloud one, is quite similar variation we have. But during the slow slip, we have this kind of the very, how to say, impulsive signal we have. Actually, we have this kind of the rectangular or impulse signals we have. This is a magnetic data. This is the electric data, so nearby. So taking account of the consideration, so the current under the ground flow, we can satisfy this kind of station. We have 3 station data, and timing of the signal is quite same, but the waveform is a little bit different. Waveform means the intensity of the and polarity in vertical component is sometimes different. So taking account of this, we conclude the water, fluid under the ground gives us this kind of rotation. So this is the electrokinetic effect, we call it. Okay. Anyway, the source of the signal is like this. Anyway, then we would like to do the statistical test. Okay, so we analyze the 10 years data from 2000 to 2010 before Tohoku earthquake. We take 100-kilometer radius from the station. So we have 50 earthquakes happen in these areas. Okay. We select earthquake satisfied this condition. The ES indicates the seismic energy received at this station one day. If this value is greater than 10 to the 8, we pick up earthquake, which we analyzed. For M4 earthquake, so radius is within 30 kilometers is the target for which analyzed. So this is a definition of the earthquake selection. And this is the date, and the 0 day indicates that the day of earthquake. Minus indicates the before earthquake. Plus indicates the after the earthquake. And Z value vertical component value exists the median value, the 1.5 IQR. This is the all data we sum up, and this value is greater than the median value plus 1.5 IQR. We call it is anomalous data, anomalous values. And the data exceeds this model value. This is a normal state. So we use this data of binary data, normal day and abnormal days. And we sum up the 50 number of earthquake day and make the histogram of the normal state like this one. Okay, so 50 days earthquake day we can count like this way. And we analyze the random test. Random test is we pick up the same number of the data, earthquake, from the old data, 10 years data. And the 50 data set we pick up. And we repeat this procedure 10,000 times and take average and take 2 sigma. And if beyond 2 sigma, there is statistical significance correlation. So this is the result. 0 days is day of earthquake before and after. And vertical is count. The left side indicates 1 day value, the right side 5 days count. 5 days count is this column. 1 day count is this blue line. For 1 day count, the significance level is red line. 5 days count, green line. For 5 days count, anyway, 5 days, 15 days before the earthquake, there are significance. We have 50 days of earthquake, which we need to analyze. And normally in data, we have 300 or more. Anyway, here, and the percentage of the here is about 60% of the earthquake we can detect for 5 days count. To evaluate this, we check the distance change. In A region is red color. In B region between 100 to 260 kilometer number of earthquakes same is black color indicated. The significance level is here. Only for near earthquake there are significance. So anyway, there are distance dependence. Also, magnitude dependence or ES dependence we can check. For ES 10 to the 8, 10 to the 7, 10 to the 6, 10 to the 4, local seismicity is investigated. Again, green line is statistical significance level. Red line and purple line exceed the significance level. Okay, so that is a very important point. Statistical significance with scale of earthquake or radius we have. It suggests the causative correlation. Other 2 points in Izu and Boso, the other 2 places with similar analysis we have done. For Boso, nearby the Kakioka station, we have 0 to 5 days, we have significance. For the Izu, that is volcanic area, significance is about 1 month before the earthquake, they give the significance. So the lead time is quite differences. Then we'd like to check the we'd like to assess the precursor information, including or not. To achieve this, we use the ROC analysis. ROC is receiver operating characteristic curve analysis. In seismic approach, usually Morchan error diagram will applied. This is a kind of the ROC analysis. ROC is given here, receiver operating characteristics curve analysis. Okay. For the Morchan error diagram, the horizontal axis is alarm date. So this is how many percentage we issue alarm. Vertical indicates detection rate. This is successful rate. How many earthquake is detected? For one indicates all earthquake detected. In this axis, one indicates all days we issue alarm. 0 means no alarm issued case. In random case is given by this green line. Okay. To simplify, to understand, if the ROC analysis is the trace is above this green line, like this way. So this is better than random guess. It means there is precursor information. If below like this, no information, no precursor information included. Just very easy to understand like this. Okay, this is I like skip. Okay. Okay. And this is a result. This is random guess. So this is a ROC test of our ULF result. Result is much better than the random guess. So it means for ULF EM signals anomaly has precursor information. So this is very important. Okay. And actually what we say before is this part. Okay. 50% of earthquake is detected and alarm rate is 30%. So this is our SEA result. See. And also, if we take the much more precisely for the ROC test, we have a confidence level. It's given here. How much differ from the random guess, or how much differ from the this confidence level is also very important. So using the this how to say somehow property gain or the difference gives us some optimum parameter to predict the forecast earthquakes. So this is one of the very important to find out the optimal parameter for earthquake short-term forecast. So this is the result for the is volcanic area and also area. We have similar result. Okay, for the volcanic area, much better performance we have. Okay, about 10% alarm rate and 40% earthquake we can successfully detect. So this is a latest result which we have done. And using the AUC area under the curve between the curve and the random guess, we evaluate the performance. If the above this guess, we gave the positive one. If negative one, if below this random guess, we give the negative values and sum up. And we check the delta and L performance of this ROC. This is a result. This is delta, lead time. This is the L, how many days we issue around. The best performance in terms of the area, 1 day, 40 days lead. 1 day around, 8 time lead time. So this tool gives us the best solutions. Okay. And actually, the 8 days lead time, 1 day around it give us this kind of solutions. Due to this, we can have some good result. And this ROC is not only related to delta and L, but also the magnitude and location and some others. So we'd like to analyze much more effectively. So we take the L days, delta days, and ES and the difference given here. 1 day and to the 200 is much effective, and ES, this magnitude greater than 8 or 8.5, 8.5 is max optimum parameter what we can get from using this kind of solutions. And we also the hand cast with given here using the optimal parameter which is used for the 2010, and we forecast 2016 data, and 2 of earthquake we can successfully detect it. For larger one, we have only 1 earthquake and we can detect only 1. So there are in probability, in the sense of probability, we can satisfy the previous probability using the optimum parameter to the actual new data. This is not true forecast. We use handcast. We observe some data and use this kind of like this way. And maybe I have time, so I'd like to briefly inform the TEC agnostic anomalies. So this is a similar approach. We have how to say statistical significance we can check. This is 0 days, and this is how to say statistical significance gives by this red green colored one. 1 to 5 days before the earthquake, ionosphere disturbed in somehow. In Japan, positive anomaly, I mean TEC value for electron density in the ionosphere increase against the 15 days backward median model. Okay, so this kind of anomaly observed significantly in Japan. And also the ROC, this is the result of ROC. ROC gives us they have information of precursor. Anyway, finally, we can say positive anomaly 5 days before the earthquake we have in TEC anomaly. TEC is integrated value of electron density between ground west receivers and satellite antenna. Okay. We use these data and we make tomography of 3D electron densities. And this is the final result. And subtract the 15 days backward median values. And then we found the electron density is not only positive, but this epicenter, just above the epicenter, below the between 200 to 300 kilometers, the electron density decreased about 60%. And the other part, electron density enhanced 200%. So this pattern is dominant in Japan. Okay, anyway, this kind of pattern we can see. And we analyze for Indonesia. You have an earthquake in Lombok 2 years ago, maybe last year, 2 years ago. Okay, we analyzed 35 earthquakes in these regions, and we have similar result. This is the day of earthquake, This is total anomaly given here. about 1 week before the earthquake, we have significance. That line is significance level. In Indonesia, you have positive anomaly and also negative anomaly. Negative is a decrease of electron densities in the target regions. Anyway, this is a very brand new result. And using GIM, GPS-TEC result. And also, we analyze the iron data using the Kokubunji data. You have also iron zone operated by LAPAN. And we monitor the electron density at the maximum electron density in the ionosphere. Okay, this varies. Okay, so this is electron density. This is the height here. We monitor change of the maximum electron density. We call this is NMF2. And due to time, I show you only the result. And we found significant abnormal in NMF2 10 days before the earthquake using the 60 years statistical analysis at Kokubunji data. What kind of earthquake we analyze? What kind of earthquake is sensitive to this kind of one? Depth shallow one. Okay, depth shallow down 40 kilometers. The epicenter distance 50 kilometers. Magnitude greater than 5.8. That is our result anyway. This is our statistical significance. And we assess the precausality using ROC analysis. And this is a final ROC, and this red curve indicates. Anyway, optimum parameter is given epicenter distance 200 kilometer, magnitude greater than 6.4, shallow one, the depth shallow than 20 kilometer, lead time 10 days, alarm period 1 day. This gives us this result. And due to these parameters, okay, for D and PG is distance between this random guess. PG is gain from this random guess. DC, PDC is this confidence level against, okay, confidence level. And the result given here. Okay, alarm rate is about 10%, okay, 10%. And detection rate, success rate is about 50%, 50%. So anyway, iron zone data is much more sensitive to the GPS-TEC, and ionosphere is very sensitive for the earthquake, and they have precursor. We can analyze the precursor signature using the ionospheric data. I extract from the LAPAN page, and you have several stations. I know Padang station and the Lamban station. I know I visit there, and you have the other station. And I don't know their operation is continuous or not, but you have a potential. I know the Padang is much more stable, but if you have a chance to analyze data, so you can get some good result, I guess. Okay. And finally, I'd like to say again, so today I'd like to say only a ULF magnetic data and GPS ionospheric data or GPS tomography. I'd like to show you. And the other pattern, the other parameters which we have, okay, VLF, LF variations, and seismic pattern, and GPS deformation, radon measurement. So there are the potential to contribute to the probabilic stochastic model. And in this model, so background seismicity, and this is seismicity also. Okay, first two term indicate the seismic pattern or seismic activity related to the stress change. In addition, we can call this kind of parameters using some weight, and we can control this stochastic model of the future earthquake forecast. So this is using this, we can extract information 1 week before, 3 days before, 1 minute, 1 day before, 1 hour before, blah blah blah, and then we can give you some better information for earthquake forecast or earthquake information new generation. Anyway, short-term earthquake forecast or pre-earthquake process is human demand forever. This is our first seismometer in the world. Actually, it was developed in China. There are records. This seismometer records Qinghai earthquake AD 138. This is world record anyway. China also attacked by the huge earthquake, and the emperor would like to control the disaster. In Japan, in 400 years ago, earthquake is controlled by catfish. This is a legend anyway. But we have this kind of the newspaper in the epoch, and they would like control this catfish using the stone. And people believe this kind of the legend a little bit. Anyway, we'd like to control earthquake, not control, we would like to forecast the earthquake. That is, we would like to understand pre-earthquake process to eliminate, to dismiss the earthquake disasters. So that is our dream. In Japan, we developed this kind of ground stations. This is multiple stations. I don't show up any sensors, unfortunately, but in this station, we have ULF electromagnetic sensors in the bottom of the ground. Today, I'd like to show you. And also the radon sensor or some meteorological parameters, the VLF sensors. So this is multiple stations. Okay. For GPS sensors, we use the sensors operating by the GIS, so which we can use freely, which is much more work. Anyway, we have this kind of station near Kanto areas. Chiba is here, okay, over here. Tokyo is here, okay, very close to Tokyo. And future large earthquake happen to expect to happen this area or these areas. This is both of. Anyway, Tohoku earthquake. This is break fault collapse around here. This is the rest of the fault anyway. So future large earthquake, M8 earthquake is expected here. And also here, after the earthquake, after Tohoku earthquake, the probability of the large earthquake just below the Tokyo is. Anyway, in our university, the earthquake forecast is very important. Anyway, thank you very much, Telemakashi, for my talk. And this is what Yudi-san told first. This is our book which we write, pre-ask process, multi-disciplinary approach to ask prediction studies. So the which is maybe a Bible for the short-term ASCO forecast or understand pre-ask forecast using the electromagnetic sensors. Okay, thank you very much for your attention. Telemakasi. Okay.
Thank you very much. Thank you very much, Professor Hattori, for giving us such informative and interesting presentation. Yeah, ladies and gentlemen, now come to the question and answer questions. Please write your question on the check box. Yeah, so you have already some questions here, Professor Hattori. So thank you very much. In the as introduction, you give us introduction about Chiba University and Japan weather and etc. Yeah, it's interesting for us, and we hope some of our students can proceed their study at Chiba University. We hope, yeah, and we have now more than 100 participants. This is a huge amount of participants.
Okay.
Registered more than 190. But you know, now we are in the semester. So the semester has begun. Yeah, we are in the third weeks now. Yeah, I think when yeah, so this is a huge amount of participant, more than 100.
Okay, thank you very much.
So yeah, you're welcome. So there are some questions. Maybe you can see also here in the chat box. Yeah. For example, this is okay later, but yeah, from Muhammad Arif Munandar to everyone. Maybe you can read this and answer directly.
Okay, so okay, so maybe this is the first question. Why a 12% day one? Okay, Muhammad Daenari san. Thank you, sir. How about the PPT material we will share also in EduEX system? Okay, maybe the how to say the capacity volume is a little bit very big because this is more than 50 megabyte is at the moment. So maybe I will reduce the something. I will send the PDF file to Yudi-san, and Yudi-san will control my presentation. Some of them I didn't publish. Maybe I will cut this slide and send you. It's okay?
Okay.
So the first question is PPT material. I can share with you, so we can do. Okay.
Yeah.
Please prepare write your question. Okay. Professor, is very interesting presentation. I want to ask how long JMA build system TE tsunami early warning system like today? Actually, very long histories. Anyway, the tsunami in Japan is anyway very problem. Not only the nearby tsunami, but the tsunami from the Alaska earthquake or Chile earthquake is we have very huge damages. Anyway, we have histories and maybe more than how years now. Anyway, more than 70 years we have struggled with about these problems. And nowadays, anyway, the ITC, anyway, nowadays we set up the ocean bottom pressure meter. Okay, and also the fiber cable, also it's possible to use pressure meters. So this kind of the technology, development of technology is very much help for the tsunami early warning systems. So every day, every year, sophisticated. In some time ago, only buoy system and the tidal gauge is only, but now ocean bottom pressure meter or the other sensors, it is also available. But the important point is, so far, there are no system to monitor the change of the sea level or sea floor. So that is very important. If we add this kind of the sensors or this kind of data in their system, so much more progress we will have. So that is my topic in tsunami early warning system today's talk. And it's very good to that the company install seismograph data. Who will maintain seismograph, GMA or company itself? This is a company. So this improvement of the early warning system is not a public one. So this is a very, how to say, private one. So some company will create this system, and the company will maintain this one with client. Okay, this is the second question. Third question, as we know, information EQ always update after EQ happen. How long JMA update EQ after this shock? After first shock, what do you mean? This is a early warning system or general earthquake info system? So which you would like to know? Okay, maybe later you can ask me. Number 4, how we can short forecast with satellite thermal weather. It is possible. In Japan, we check the Himawari data. We can analyze thermal anomaly related to the earthquake. We have they pass the statistical significance and ROC test. So they have the information of precursor. So there are chance to involve the system. So we can use the satellite forecast. But this anomaly is not only before the earthquake, but after earthquake or some anomaly, it happened. So a little bit difficult, but generally it is possible to use. So this is the fourth question. Okay. I want to ask you how wide the potential radius electromagnetic instrument can cover electric data to create earthquake forecast in the area. And it depends on noise signal to noise ratio at the station. In Japan, about 100 km radius of the station for URF measurement. For the satellite, ionosphere, maybe 300 kilometer is available to use. So it's general one, I think. So for the magnetometer, so it depends on local electromagnetic environment. In Tokyo, no chance, okay, because of the many train is going through even nighttime. Okay. But in the countryside, usually 100 or 200 kilometer is sensitive detectable distance, generally speaking. Okay, this is a number of general EQ, PQ っていうのはさっきのあれだな、general EQ. For the information on the intensity and how much area is vibrated, is maybe actually 2-3 minutes after the quake or 5 minutes after the quake, they can calculate, they can collect the data. Maybe it depends on communication system and server system in your countries. Maybe the BMKG has similar system, and the BMKG has take a role of the issued information. Okay, other questions? Maybe I answer the all question by chat. Any other questions?
Yes, Prof.
Okay.
Okay, thank you. The time for me, ladies and gentlemen. First time, I would like to introduce myself. My name is Muhammad Zainal Iksan, and I'm from Central State University, China. Thank you very much for your explain. I think it's very interesting. And I'm here. I want to ask about as we can see that in every earthquake or tsunami in Japan, the number of people who become victims is small compared to the number of victims in other countries such as China, Thailand, Indonesia, and others. I see that the Japanese government has given instruction and preparations made for its citizens. Then what is the government doing or the residents are preparing to welcome the earthquakes so that the number of victims is less? Can you please explain to us, for example, where do residents take shelter because earthquakes and tsunamis can destroy whatever it goes through? Thank you very much.
Okay, thank you very much for the questions. Anyway, we have several experience of the tsunami, and once how to say people killed because of tsunami, the government consider the regulation of the bank or something like that, and after that, immediately they create new bank to protect the tsunami systems. Okay, so anyway, that is the main differences. But if the tsunami is beyond what we expected, which happened in Tohoku earthquake, so we killed very much people. Okay. Anyway, within the expected, our system is very safe. That is not only in Japan, but also everywhere. And once decided, this is a regulation in Japan. So Japan government or local government try to satisfy this regulation, not only the seashore, but also building also. So if you come to Japan, you can see many buildings with additive columns, or some column is with iron plate. So this is protect for shaking, earthquake proof, something like that. So this kind of activity or this kind of regulation is strictly Japanese company or Japan government control by law. So I think this is the reason. And also the construction company follow this regulation. So this is, I think, the very important point. So strength of structure, strength against tsunami, architecture is one of the very important things. But the tsunami power or earthquake power is greater than what we expected, so which we have also damage. Okay, so the how to not control, how to obey the regulation is maybe the important.
Okay, thank you very much for your explanation. But here I want to ask about where the resident or people take shelter, because I think earthquakes earthquakes and tsunamis can destroy whatever it goes through, right? So where the shelter Japanese or people in Japan to attack, to save themselves. Thank you.
Okay. Anyway, the other thing is education. Okay. Once very severe shaking is we felt nearby seashore, we Japanese escape from to the higher place. Okay. So that is also very important. So this is education of Japan system. For me, when I was kindergarten or elementary school, teacher told, so when you go to the seashore and you felt earthquake, you need to go to the hill. You have to escape from hill because of the tsunami. Better tsunami is coming. Okay, so this kind of the education is very important. In Japan, we have exercise of the evacuation of the earthquake. We have elementary school every year. We have this kind of experiences or practice. In university, we don't have. But for elementary school, junior high, we have every year. We have this kind of evacuation experiences. I think after Andaman earthquake, your Indonesian people, Indonesian school has similar exercise or review practice in school. I heard from the BMKG. So anyway, this kind of the education is also very important. Not only the structure, but also education is very important. In this sense, forecast is also very important. What kind of information you can receive, how to react. So this kind of the how to say simulation in the brain or practice before earthquake is very, very important to mitigate the earthquake disaster or tsunami disaster.
Okay, well done, Prof. Thank you very much for your answer.
Okay, thank you, Mr. Zainal Iksan. Thank you, Professor Katsumi Hattori. Yes, I think time is over because Professor Hattori must leave this meeting to another meeting, I think. Yeah. So before we finish this session, we will take photos. Maybe Ms. Rifa, could you organize it?
Okay.
Please.
Now is photo session. To all participants, please open the camera. Okay, we will start. Take a picture together on a screen. Okay, the first page, I will take a picture. And then now a second page. And then third page. Fourth page. And the last page. Thank you. We have photo session together.
Okay, thank you, Rifa. So, ladies and gentlemen, we finally come to the end of this session. I'd like to thank the speaker, Professor Hattori, for the informative and interesting presentation, and all the participants for the very active participation. So, thank you very much for all. And on behalf of our department, we thank you very much for your attending this course, for you, Professor Hattori, and for all attendants. Thank you very much. And we will It will be in this room again tonight from 19 to 21. So don't forget to join us, and we will start with first quiz in this evening. So don't forget to join us at 7 o'clock p.m. Okay, thank you very much for all. Thank you very much for Professor Hattori. See you again next time. Thank you.
Terima kasih.
Terima kasih.